The purpose of today's presentation is to provide a high-level overview of emerging water contaminants. We'll focus on PFAS, and we'll talk about the public health and environmental concerns. Our presenters are Hatem and Tom. Hatem is a senior project engineer at our headquarters in Baltimore, and he focuses on municipal and industrial water and wastewater systems. His experience includes the design and evaluation of BNR systems, biowind modeling, treatment systems, and residuals management. Tom is our water and wastewater technical leader in Greenville, South Carolina. His experience includes biosolids management studies and operational consulting services. Before we get started, I'd like to point out that you may submit your questions during the presentation using the Q&A button down below. We will attempt to answer your questions during the presentation, and we will also have some time set aside for questions at the end. With that, I'll turn it over to Hatem.
Thank you, Mehmet, for the introduction, and thanks everybody for joining us today in this webinar. Our agenda for today, we will start with a brief background about the status of contaminants removal from wastewater. We will then go over the how we excelled or what we have excelled in, and talk about how the emerging contaminants started drawing our attention in recent years. Then we will provide a general overview of emerging contaminants. We will talk about the history and status of pharmaceutical residuals that have been the focal point for researchers for the last 10 to 15 years, and how the Per and Polyfluoroalkyl Substances, or in short, PFAS, got to our attention in recent years. After that, we will delve into some basic information on PFAS, their sources, their chemical structures, their properties, how they find their ways to our drinking water sources, and the potential health risks they may pose on humans. Following that, we will talk about the regulatory landscape of PFAS in the US and potential impacts on our water utilities. And finally, we will conclude by providing some recommendations on how to approach the issue if PFAS is detected within within your jurisdictions, how to approach your community, how to approach the media and other stakeholders. So starting with the Clean Water Act, the CWA, and the Safe Drinking Water Act, the SDWA, these two acts have been around for many years since 1970s to protect our nation's water. The successful compliance with these acts resulted in the development of a wealth of technologies and processes that can provide superior removal efficiency of conventional contaminants, such as BOD, TSS, nitrogen, phosphorus, to name a few. It also can produce high quality water suitable for reuse, and consequently, it minimizes or eliminates the adverse impact of these conventional contaminants on the environment. So this is a great achievement. Let's pat ourselves on the back for a job well done. Unfortunately, our job doesn't end there. The recent advances in sciences and detection technologies have allowed us to detect other micro or nano contaminants of concern that were not previously detected. It also increased our ability to recognize their long-term toxicological effects. That increasing visibility leads to increasing awareness and consequently increasing scrutiny by the media, by the general public, the environmentalist groups, and the scientific communities and regulators. In the next few slides, let's explore some of these micro or nano contaminants of concern, also called as emerging contaminants. These emerging contaminants include a diverse group of natural and man-made chemicals that were introduced to our daily lives, such as pharmaceuticals, personal care products, hormones, PFAS, and so on. The ongoing scientific and clinical research suggests that they may have some potential to cause ecological and human health impacts. In this presentation, we will focus on two groups, the pharmaceuticals and the PFAS. While the pharmaceuticals have been the focal point for researchers and regulators for the last 10 to 15 years, the detection of PFAS near industrial plants and on military bases in recent years started gradually to capture the attention of the media and the scientific community. But that increased awareness and scrutiny does not necessarily lead to immediate regulatory action. Take, for example, the case of the pharmaceutical residuals. In 1999-2000, the USGS tested for 95 pharmaceuticals and hormones in 139 streams in 30 states. They found in that study that 54% of the streams has more than 5 contaminants, and 13% of the streams has more than 20 contaminants. In another study that followed that, a joint study between the USGS and EPA in 2017, they ran another test on drinking water treatment plants, and they found 118 contaminants in 25 plants. Moreover, the contaminant candidate list number 3 that was released in 2009 and the contaminant candidate list number 4 that was released in 2016 identified some of those chemicals and nominate them for EPA to basically do further analysis on them and add them into their regulations. Nonetheless, EPA determined after further review and analysis not to regulate any of the pharmaceuticals listed in these lists. Similarly, when the World Health Organization, WHO, reviewed the limited monitoring programs on human exposure to pharmaceuticals, they found that it is very unlikely that exposure to very low level of pharmaceuticals in drinking water would result in an appreciable adverse risks to human health, as the concentration of the pharmaceuticals detected in the drinking water are several order of magnitude lower than the minimum therapeutic doses. We're talking here about a concentration typically less than 0.1%. They also found some knowledge gaps when it comes to the assessment of risk to human health from long-term exposure to these chemicals and the possible combined effect of a mixture of chemicals on human health. Therefore, the development of a formal health-based guideline values for pharmaceuticals in the WHO guideline for drinking water is currently not considered to be necessary. These examples clearly suggest that the process of regulating new emerging contaminant could be a lengthy one and may take some time before a decision is made. Tom is going to walk us through the regulatory landscape regarding PFAS in a few minutes. But before that, let's explore the properties of PFAS, how they got to our drinking water sources, and the effect that they may have on human health. The PFAS family of chemicals have been used in manufacturing and commercial products in the US since the 1940s. Nowadays, they consist of more than 4,000 chemicals. They can be found in non-stick surfaces of cookware, stain-resistant products like the 3M Scotch Guard carpet and upholstery protectors that we use in our daily life, fast food packaging, firefighting foams, pesticides, paints, photography, and so on. We're going to show a poll right now just to gauge you some of the information, so you can answer this question here on basically which one of those items you think poses more risk to human health. You may select more than one, and we will see the results in a little bit. So I think we have enough responses now. We can look at the results. So as you can see here, the majority, about 66%, they're basically selected pesticides. And then the non-stick cookware, that's the runner-up. And actually there's the firefighting foams as well. So as you can see, there is a variable opinions about which one can cause harms. And we don't have a direct answer right now, but as the research goes on in the future, we may figure out exactly which one has more impact and how best to treat that. In the next slide, we will show the chemical structure of two chemicals, and these basically we presented them here as representatives for the PFAS family. The first one is the perfluorooctanoic acid, PFOA, and the second one is the perfluorooctane sulfonate, PFAS. For those who are not familiar with organic chemistry, the F here, basically that represents the fluorine atoms, the O for the oxygen, the H for hydrogen, and the S for sulfur. As you can see to the right, these single lines and double lines, these are basically the chemical bonds. And where the lines are intersecting, these are basically the carbon atoms, and these atoms were basically removed from these images just for clarity. So looking at these two charts to the right, we can notice two main properties. The first one is that there is a lot of fluorine to carbon bond in there. So there are a lot of fluorine atoms attached to the carbon atoms. And in organic chemistry, this is considered one of the strongest chemical bonds between atoms. And that basically rendered these chemicals as very hard to treat, as we will see later on through this webinar. The other thing that we can see here also is the long chain for these chemicals. In the left side, we will see the carbon fluorine atoms, and as we said, this is unreactive, and it's basically hydrophobic to and oleophobic to the water and any polar groups. And to the right, we will see the carboxylic group on the PFOA and the sulfonate group in the PFAS, and these basically are rendered as very easy to react with water, and basically they can attach to the water. With this chemical structure, that gives us just clear indication that there is some kind of resistance to degradability or, and reaction with polar groups.
Tim, we have one question that came through Q&A. John is asking what you think is the most harmful use of PFAS, in your opinion. This is the polling that we just did.
It's really hard to tell right now what's the most harmful use, but the previous poll that we had, it shows that it's basically everywhere. Like if you look at the cookware, if you look at the stain-resistant coatings, they're everywhere in our life and we're exposed to it. The problem would be basically is the amount that we are exposed to. Is it really posing any impact, any risk to our health, or it is in a very small, minute amount that basically it's not going to be a cause of concern for us? So we'll let the research community and the scientific community basically to look into that and give us some more insight into that. But to date, we really can't identify a single source that has more impact on human health. I hope I answered your question, John.
We have one more question that came in as you were answering that one. The question is, can you explain how pesticides contain PFAS?
That I'm not sure of. I can look into it and get back to you on that.
That sounds good.
Okay. So in this slide here, in the illustration to the right, we can see it basically depicts how the PFAS get into our drinking waters. On the top left side, basically that represents direct discharges into drinking water source. You can see it coming out from factories where PFAS is being manufactured or used. Also, it can be coming from releases from areas where firefighting foams are being used, such as the military bases, airports, and other sources. It can also come as a leachate from landfills, where basically waste that contains PFAS is being buried there, and basically over time it would leach and go back to the drinking water source. Once it gets to the drinking water source and is consumed by humans, it may find its way to the wastewater stream and then gets into our wastewater treatment plants, where either it's going to be passing through the treatment plant untreated, depending on the treatment technology in place, and goes back to the drinking water source, or if it is captured and transferred basically from the liquid phase to the biosolids, and that biosolids is land applied, it may, with surface runoff, leach from the land application site back into the drinking water source. And that's why it's called, like in some scientific arenas, as forever chemicals, that it is there. Like no matter where you send it to, it's there until they find a way of degrading that chemical instead of like transferring it from one form to another. So in the next slide, we can see that basically based on the limited comprehensive studies on the impact of exposure to PFAS on human health, it basically suggests that the PFAS may affect men, women, and newborn babies. Additional studies are still underway in this area to assess the impacts from short-term exposure, long-term exposure, and the form and from the possible combined effect of a mixture of those chemicals altogether. Now I invite Tom to walk us through the second part of this presentation. Tom?
Thank you, Hatem, and welcome to everybody who's out there listening to us. So I want to, with that backdrop about PFAS, about what it is and how it's come to our attention, I want to turn our thinking towards the regulations and what's happening. What's the regulatory landscape look like with regard to PFAS in the country? And before we look at specific programs, I wanted to kind of give a framework or a backdrop for how any emerging contaminant or new contaminant is going to be regulated in the current environment. And so, as most of you may be aware, most of the environmental regulations are driven from the federal level and administered by EPA. And our two major water utility acts that impact us in this industry are the Clean Water Act and the Safe Drinking Water Act, which Hatem mentioned both of those earlier on as part of our success story in cleaning up the waters of the U.S. And so, through these acts, there is a mechanism for including new contaminants into the regulatory framework, but it's going to be a pretty long process, and I'll explain how it works under a couple of these just really briefly. So under the Clean Water Act, and that regulates our wastewater discharges and our biosolids disposal from publicly owned treatment works, or POTW facilities. So those are generally operated. Those changes would be incorporated through the mechanism of NPDES permits. So those are the discharge permits for the POTWs to be allowed to discharge to surface water. And so the limitations under NPDES permits are generally driven by water quality considerations. So there might be human health considerations, there might be aquatic life considerations, and all those water quality criteria are set either by EPA or by the states, and then those become the criteria by which the discharge permits for the POTWs are set. And so there is a mechanism in there for EPA or the states to set a water quality criterion with respect to any one of these PFAS chemicals. A second way that they can regulate the PFAS is through what's called technology-based requirements. So there's a set of standards, and they're known colloquially as the categorical standards because they address limitations for a number of categories of industries who may be discharging wastewaters either directly to surface water or to a POTW. And so where it impacts water utilities most directly is through the indirect discharger standards, or the pretreatment standards that are in the categorical guidelines. And so there's an opportunity there for the government for the EPA to regulate what chemicals are allowed to be introduced to the POTW. So there's an opportunity there. Now, in terms of the time frame, they tend to run on a 5-year cycle. Both NPDES permits themselves are renewed in a 5-year cycle. And so for any individual facility to get a new limitation on a new chemical, it's probably going to take at least 5 years for that to work through. And that doesn't include whatever time it takes for the states or the EPA to establish the water quality criteria. Similarly, under the technology-based requirements, the categorical standards, every 5 years, the EPA proposes new industries that they might want to regulate under the categorical standards, and additionally, they propose new chemicals that they may want to regulate in that. But it is at least a 5-year cycle from the time that they propose those until the time that regulations are actually promulgated. Moving on to the Safe Drinking Water Act, looking at the drinking water side of things, it's actually a little bit more of a structured process there. But again, it's a 5-year cycle. And so Hatem already referred to the CCLs, the contaminant candidate lists that are published every 5 years. There was one in 2009. The most recent was in 2016. And in those CCLs, EPA will publish a list of somewhere between 5 and 30 chemicals that they're proposing to consider for regulation. And then that will go out for public comment, and they'll receive comments, and they'll look at scientific evidence, and then they'll come out with what's called a regulatory determination. And what they say is, so they'll put out a preliminary one that says, here are the chemicals out of this list that we published originally that we propose to pursue regulation for. And you can often find, for example, in the CCL3, they published a list of a dozen or so chemicals at that time, and when they came out with their final regulatory determination, they said, we're actually not going to regulate any of these. In the most recent one, the 2016 one, they did include some PFAS, and we'll talk about that in a little bit more detail. But following the regulatory determination, then there's also going to be some time for gathering additional data, perhaps through the unregulated contaminant monitoring regulations. So they may be wanting to have drinking water facilities collect a bunch of data. They need to analyze it and see what the impacts are, what the risks are, and so forth. And then there's going to be more public comments and Federal Register publications and all that sort of thing. So you get the sense there, this is a long process that it takes for any new contaminant to be included in either one of those major federal regulations. And so there have been some attempts recently to streamline and accelerate that. And so Congress has introduced a couple of bills this year under the TSCA, the Toxic Substances Control Act, and also CERCLA, the Superfund Act, to try to mandate regulation of some PFAS chemicals. Neither of those have moved anywhere yet, but that could be a mechanism for enacting the regulations on a shorter time scale than what's built into the major federal programs. And so that brings us kind of down to what happens at the state level then. And as you may be aware, the federal regulations govern the minimum standards of the states. So all the states have to comply at minimum with the federal regulations, but they also have the latitude, if they choose to do so, to enact more stringent regulations. And so what we're kind of seeing in PFAS, in the PFAS environment, is because the federal wheels take a long time to turn, a lot of the states are acting based on local conditions, and they're enacting their own regulations. And so we'll take a look at that in just a second, but I did want to, now turning back to the federal landscape, kind of set the stage for what is guiding the states to the extent that the federal government has provided that guidance. So looking back to 2016, this is going to be on the drinking water side because that's where most of the activity is happening. And I believe it's primarily because that's the primary pathway of exposure for people right now, is through drinking water. So back in 2016, EPA issued a drinking water advisory. And so this is an advisory, it's not an enforceable standard, but they said at that time, we recommend maximum exposure of 70 parts per trillion of these two combined chemicals, PFOA and PFOS. Those are as Hatem mentioned before, those are kind of the representatives of this class. They've been around for the longest, and we kind of know the most about those. Although, as an aside, in industry, those have largely been phased out because of the recognition of some of these issues, and they've moved to different PFAS chemicals to accomplish the same things. But there's a lot of that out there already, so in terms of residual and long-term exposure, there's still a risk. Coming forward a couple of years, EPA performed a drinking water study looking at 25 different plants and looking at a number of PFAS components in there. And what they found was about 20 parts per trillion in the source water in general. But what's important about this study is you look at the treated concentration, and it's really not a whole lot different than what went in the front end of the drinking water plant. And so that's starting to establish this idea that our conventional treatment technologies that have worked very well for us in terms of most of our health goals for our customers actually don't seem to be very effective for removal of PFAS. And so when we talk about treatment later, we'll talk about that a good deal more. Then looking at this contaminant candidate list number 4 that we mentioned previously, the 2016 was the year that was issued, and that's the most recent one that's been done. So the EPA did make a preliminary determination that they're going to regulate PFOA and PFOS. Now, regarding time frame, though, you might be interested to know that the CCL4 was issued in 2016. It was not until early this year, 2020, when that preliminary determination was actually made. And now we're still in the period of receiving public comments on the preliminary determination, making a final. And so you're almost 4 years out from the time that that CCL was issued. And you can imagine there's still going to be some time that's going to have to elapse once they receive final comments and make their final determination before they actually are able to enact any of those regulations on PFOA or PFOS. So that's on the drinking water side. There is a little bit of movement on the Clean Water Act side. That's this last item here. In 2019, which is part of that 5-year cycle we talked about, with EPA looking at new industries and new contaminants to regulate under the technology-based standards, the categorical standards, they did include a study of these industrial sources of PFAS, but that's really kind of just a baby step towards implementing anything on that side. And so you can expect that's going to take even longer to work its way through the regulatory process. So with that, we're going to turn to the states. And so I wanted to put this map up here to kind of give you a perspective. What does PFAS look like across our states? So you'll see a bunch of blue dots. Those represent some drinking water sources that have detected PFAS in them. There's a few, you can see some purples in there as well. Those are the military sites where it's been found. And then we've got a few other miscellaneous sites around there in orange. Now, what we don't need to conclude from this is that there's a handful of states that have a big PFAS problem and the rest of us are in good shape. What we're really seeing on this is the specific states where PFAS has come to their attention, and they've taken a much more aggressive stance towards quantifying and trying to regulate PFAS in their areas. And so if we came back to this map maybe in 5 years and started looking at, okay, where have people detected PFAS, I suspect you're going to see a much more even distribution across a lot of states where people have started where more of the states actually start looking at it, probably in response to some of the regulations from the federal level. So what you need to see here is there's a handful of states, primarily, on the East Coast and the Northeast, North Carolina, Michigan are a couple of big ones. And most of those states are ones that have major manufacturing facilities producing PFAS or the PFAS chemicals. They're also the ones that have a lot of military bases. So Colorado's probably one of those represented there. And California's probably got a pretty good mix of military and industrial production. So largely the detection and the looking and the investigation for PFAS has come in response to environmental issues that have arisen related to the production of PFAS. So on the next slide, I just have a table here to kind of give you an idea of what the landscape looks like from the state perspective. And so one of the hallmarks of what's happening in the states is it feels kind of piecemeal and disjointed because every state is taking a response based on local conditions. In some cases, they're being guided by the federal guideline of 70 parts per trillion, and in other cases, they're kind of taking their own route. And so you can see here that, for example, Connecticut, they've given a sum of 70, but that's not only PFOA and PFOS, those first two columns, but it's also including some of these other PFAS compounds that are coming under scrutiny. Others, like Massachusetts, has ratcheted that down a good bit, and they've gone down to 20 for the sum of a number of them. Others, North Carolina, for example, although they're dotted with PFAS detections all over the state, they've just gone to this one chemical, the Gen X out there, which may be one PFAS that you've heard about in the news, and they're just looking at a health advisory of 140. And so you've got this real, I would almost call it a jumble of approaches, of regulatory stringency. So to look at this and try to predict what the landscape's going to look like in 5 years is very difficult because we don't have an overarching federal approach that is really driving this, and it's being driven by the states instead. Eventually, something's going to have to be harmonized to to address this across the entire country. And so in the meantime, depending on your locality, you may be subject to a different set of requirements than someone doing the same thing you're doing or facing the same issues that you're facing in another state. Now, having said that, there is an indication based on the levels of limitations that we're seeing here, which are all in parts per trillion, that we're going to have very stringent limits, whatever they are. Because if you're familiar with water utility limits, most of them are in parts per million, right? Milligrams per liter. In some cases, for chlorine and some other substances, we may get down to the parts per billion. So the idea of a parts per trillion limit is very strict and stringent. So that's the one thing we can predict about this going into the future. And so with the regulatory picture in mind, we're going to kind of turn our attention to how is this likely to impact water utilities. And so we're going to look at a couple of time frames here to try to talk about, in short term, what might be an impact to your utility versus medium term or longer term. And so by the short term case, I'm really talking about probably a 0 to 3, 0 to 5 year time frame. As the PFAS starts to get a little bit of traction, but there's really not a lot of direction to how things are being pursued. So in the short term, media attention is probably going to be the first issue. If you watch this issue in the news, you will have seen that probably almost a day doesn't go by somewhere where somebody's publishing an article about PFAS somewhere across the country. And so media attention is going to be one of the short-term impacts. Once that media attention becomes focused on a particular utility or in a particular area, then there's going to be necessity for additional customer and stakeholder communications. And we'll talk about that at much more length towards the end of the presentation. One other thing that's likely to happen, though, in the short term, whether it's driven by federal requirements under the UCMRs or whether it's driven by state requirements, or individual utilities may elect to do it on their own because they want to be out front of this. And that is that there's likely to be increased monitoring. So whether you're on the drinking water side and you want to look at your source water, you want to look at your drinking water quality, you want to look at your sludge, or if you're on the wastewater side, you might start looking at influent, effluent, biosolids, and so forth. Or you may be mandated to do that by your state. So those are going to be probably the shorter term consequences. Moving out to a 3 to 5 to 10 year frame, what I'm calling the medium term frame, I think there's going to be more scrutiny of biosolids quality and the disposal methods. In other words, they're going to start looking at the wastewater treatment plants, the POTWs, and what's happening to those biosolids. We have Class A biosolids going to public distribution. Maybe we have some Class Bs going to land application. And what if we have PFAS in there? People are going to start looking a lot closer and saying, okay, is this becoming a major route of PFAS to get into the environment? I think there's also in that medium term going to be an opportunities for some source reduction. As we talked about a few minutes ago, the wheels of the federal regulatory apparatus are kind of moving slowly. And so you're probably not going to see them in the categorical standards for a number of years, but there are some opportunities via local limits. When you're creating your pretreatment program as a POTW, you have the option to create and set local limits that you can enforce across all of your customers, including your industrial customers. And so there could be an opportunity to remove some of that before it gets to the POTW. And in most respects, that's the best way to handle it because you can get it before it gets too diluted. And the people who are generating it probably are the ones that ought to be treating it anyway. So that's our picture in the medium term. And then moving into the long term, this is where it gets very hard to predict exactly what's going to happen. But I think we still have we can make a pretty good educated guess about what this is going to look like. So I'd already mentioned there's probably going to be additional scrutiny on the biosolids. And so we've got some beneficial reuse options that many of us have been trying to pursue, and they've been good for our utilities and they've been good for the environment. But there's a potential that some of those are going to get lost or at least highly restricted if PFAS starts being detected in everybody's biosolids. So we don't really know what it's going to look like, but I feel like there's at least a risk that some of these options are going to get lost for us. And so that means people who are depending on those methods for getting rid of their biosolids are probably going to have to look in a different direction. Which brings us to the next point. It's possible that landfill disposal or the landfills could impose additional restrictions. Back on Hadam's FATE slide where he was showing different routes of getting PFAS into the environment, landfills were one of them. And so if landfills come under scrutiny, they start getting regulatory limits put on them, they're probably going to pass that back to their customers and either limit or at least or totally restrict the receipt of things that are known to have PFAS in them. And so that could include biosolids. There's other issues with biosolids landfill disposal anyway, such as slope stability and some other things that are totally unrelated to PFAS that is making landfills not so willing to receive it also. And so I think those things will probably play in tandem and possibly make landfill disposal more difficult if that's what option you're able to do. I think there's potential for requirements on end-of-pipe treatment, but at the scale that it's got to be accomplished at a public utility, it's going to be very costly. And we'll talk at much more length about treatment in just a few minutes. But lastly, in the long term, there's this question mark out there. Are there going to be legal implications about the people who have created and generated this, the PFAS? So if any of you are familiar with Superfund and how the liabilities attached to anybody who has disposed of those materials that have caused the environmental degradation, even if they were in compliance with the disposal regulations at the time they put it in the ground or that it became a contaminant, there's still an avenue for them to be legally responsible and financially responsible for the cleanup of that material. And so what happens if we have a legal theory that emerges around PFAS that has kind of the same idea? So if you've touched the PFAS at any stage of its disposal, so you've received it from an industry and then you've discharged it to the environment, could there be a circle-like liability? We don't really know right now, but that's another risk that's out there for the long term.
We have a question that came in. The question is, what are safe ways to dispose of biosolids?
So if the question is related to biosolids in general, any of these routes that I mentioned here, our Class A distribution, land application, and so forth, those are all good, safe ways of getting rid of biosolids conventionally. If the question is related to how do we get rid of biosolids with PFAS in them, I'm actually going to defer that for just a few more slides because we're going to start talking about treatment, and I've got a whole section talking about how do we treat biosolids with PFAS in it. Does that answer the question?
I believe so for now. Thank you.
Okay, very good. Thank you. So let's move on to the treatment question. So as kind of a framework to help guide our thinking here, there's some things that are going to impact any treatment technology that we try to approach for PFAS. The first is we're going to be looking at a very complex regime. As we've already noted, conventional treatment technologies like sedimentation and filtration in a water plant or activated sludge biological degradation in a wastewater plant don't really impact PFAS. The bonds are too strong, as Hatem noted. We've got very strong chemical bonds there. But another complication is because we're at such low limits, parts per trillion, there's going to be interferences from a lot of other stuff that's in that wastewater or that water. And so if you're familiar with any, for example, oxidation processes, oxidants like chlorine tend to be preferential towards certain compounds, and it takes them longer and it takes a higher dosage for them to be effective for other ones. And so because we're talking about such low concentrations of the PFAS in these streams, and you're probably got other things in there at the parts per billion level and the parts per million level that aren't really harmful, but they do scavenge your oxidant or reduce the effectiveness of your treatment on PFAS, that's going to be a complication. Another issue is because we can't use our conventional well-known treatment technologies, most of the technologies we're looking at for trying to attack PFAS are in their infancy. So much of it's in the research and development stage, and it's really not ready for large-scale implementation. And lastly, all the approaches, or most of the approaches that we're looking at right now are actually we're just sequestering it. We're moving from one media to another. So we might be taking it out of our water, but we're moving it into a solid phase. And so we're not really destroying it. And so there's really a question out there. We don't know the answer to this, but it could be a kick the can. We could be digging a hole in the ground, moving it from our liquid, putting it in a solid and sticking it in that hole, and then not realizing in 50 years, all of a sudden we've got this stuff leaching out, or there's issues we didn't comprehend when we started doing it. So we need to be kind of cognizant of that as we approach the idea of treatment. So we're going to move on to the next slide. It looks like we have a question here.
I think the
that-
question is related to what you are going to cover in the next few slides,
Okay.
or maybe you just answered yes.
So looking at the liquid side of things, so this is our water and wastewater technologies. So I think I kind of alluded to it earlier, but a lot of these treatment technologies are species dependent. In other words, they work better for some compounds than they work for other compounds. And because PFAS is this broad range, this broad family of 4,000 compounds, you can imagine that some of these technologies may be effective for certain ones and not effective for others. And so if you're a water utility who's having to treat for it, or if you have an industry who's having to treat for it, the effective treatment may vary depending on what they're producing and what they're discharging. The second thing we need to think about is you're going to have to pre-treat this water to a very clean level to start with, because for example, these two technologies I've noted on this page, granular carbon, ion exchange, they require very clean water or else they're going to foul. And not only that, but if there's a lot of competing contaminants in there, again, they're going to exhaust more quickly, and it's going to potentially increase the number of columns that you need, or the number of times you have to change out your media, or so forth. And so the cleaner we can get this stuff of all the other contaminants before we try to put it into a treatment for PFAS, the better that's going to happen. And so these are a couple of the front runner technologies for PFAS removal, and they have been shown to be effective in groundwater treatment. But we've got a couple of things we've got to deal with those, and it's really going to affect almost any of the technologies we're talking about on the water side. And that is, you've got media that gets exhausted and has to be either disposed of or regenerated. And so again, if we're moving our PFAS from the water to a granular activated carbon particle, and those are being taken out and disposed somewhere, that may be more stable there than it is in the water, but I mean, what's our long-term impact of that? And to some degree, we don't know. Or if we're going to regenerate that media, so we're putting it into a high temperature process to reactivate the granular carbon, or you're putting it through kind of an acid wash on the ion exchange to release everything that's been attached to it. And so you're creating this concentrated stream with PFAS in it that you're going to have to figure out what to do with. So those are some of the unknown questions right now. How are we going to handle that? And so, for example, coming onto this next screen, reverse osmosis is another one that could be pretty effective and has been demonstrated, for groundwater treatment. But one of the big issues with RO, if you're familiar with it, is that it creates a concentrated reject stream. And so a lot of places where you've seen reverse osmosis deployed in the water utility industry is for treating brackish water out of groundwater to remove salt, or for desalination out of the ocean. And so in those scenarios, it often doesn't matter that you've got 10 or 25% of your stream that has to go somewhere, because it's just the basically innocuous components that you just took out of your source that you're just going to put right back in your source. And it's not as big of a deal there. But if you're looking at a concentrated reject stream that has PFAS in it, and let's say we're trying to deploy reverse osmosis on the scale of a water utility, even a small one, 2 million gallons a day. And so at 10%, you've got a 200,000 gallon a day concentrate stream coming off your reverse osmosis system. What are you going to do with it? And so it's a really difficult question to answer. So even if we show it to be effective for removing PFAS, then we've just moved it into another place and we're not sure what we're going to do with it then. So as we move down this list here, we're moving into more advanced and less developed technologies. Advanced oxidation has been used effectively, for example, on water utilities for taste and odor removal. And so in that sense, it's not a new technology, but when we're applying it to PFAS, its effectiveness on the various components and so forth is still not really known. And so it's not developed for a large scale use with respect to PFAS. And then we move down to this next list, electrocoagulation, carbon nanotubes. We're moving a little closer to science fiction than we are to science fact on those. They're still in the research and development stage. And so what those look like on a large scale is just speculation at this point. So I added this note at the end that says most likely to exceed, and I'm really referring to your budgets, because any of these treatments that we're talking about, particularly if we're going to deploy them on a large scale, not only is the equipment expensive, but operations are expensive. And so that's a consideration that's going to have to be addressed if treatment technology at the water utility level is going to be pursued. So let's turn from the water side of things, and now we're going to talk about the biosolids. So there is some good news on the biosolids front, actually, and that is thermal treatment seems to be kind of the front runner for biosolids treatment. And we can actually destroy the PFAS molecules if we can get it up to 1100 degrees C. Now, there's a lot of energy involved in that, but the good news is we can actually destroy the PFAS. And so some of the approaches that could be taken for thermal treatment of biosolids would be incineration. So here we're talking about thermal destruction in an oxygenated environment. And incineration is not a new technology. It's been proven and it's been used a lot. But one of the things that will become a consideration for deploying that for PFAS is, there's fewer incinerators in operation now than there were 40 years ago. And there's a reason for that, because people don't like them in their backyards, because there's still some environmental issues related to incineration. And of course, there's a lot of costs and so forth. And so the idea of trying to turn around opinion about incineration and deploy it at a large scale for PFAS treatment is going to have its challenges. So one of the newer emerging technologies related to biosolids is pyrolysis. And some of you may be familiar with that because a lot of people are excited about pyrolysis, but it's basically just the thermal destruction in an oxygen-free environment. There's potentially some energy advantages to doing pyrolysis rather than incineration. But in the end, we're still looking at the same thing. And in public eyes, and when it comes to regulating pyrolysis, people are probably going to think it's really pretty much incineration. And so there may be similar objections to deploying that on a large scale as well. We do have one last note there, and that is it's actually happening now. People are disposing of their biosolids in cement kilns. And so many people are doing it now just for sustainability reasons, because it's better than putting it in a landfill. It's better than it's better than a lot of other alternatives. The biggest issues with the cement kilns is capacity. If we try to institute treatment of PFAS-laden biosolids on a large scale, there's just not going to be enough capacity in cement kilns to really address it. But it is an effective way of treating it. And it's a sustainable approach because you're turning it into a beneficial or useful product at the end. So I've already mentioned some of these challenges that we're facing from the treatment standpoint, but this kind of sums it up. So we've got high energy demand from these technologies, and that energy demand is really going to work counter to a lot of other things we're trying to accomplish in our industry. So at the very basic levels, we're trying to reduce our treatment costs. Power consumption has been a focus of our attention for a lot of years, and now we're talking about carbon footprint, and maybe we've got other sustainability goals. And unfortunately, most of these technologies kind of work counter to that. So we've got to make some adjustments if we're going to be using and developing some of these for PFAS removal. Secondly, I've alluded to this idea previously, but permitting is going to be a challenge because we've identified some effective technologies, for example, that can destroy PFAS and biosolids, but being able to actually permit a substantial number of these facilities is probably going to be a difficult challenge. And then lastly, I would say because we know so little right now about what happens to our byproducts and what happens when we put PFAS on carbon and then we go dispose of that somewhere, are there going to be some unanticipated consequences we haven't thought about? So like turning back to our idea of incineration or pyrolysis, what if we have some combustion byproducts of PFAS that end up in the air and we can't get them out with a scrubber and we can't get them out with our typical stuff, and it turns out that those have undesirable environmental impacts. So there's going to be things like that we're going to have to deal with, and we don't even know what they are right now, right? We're just trying to ask the questions, but as the landscape kind of gets clear and the fog clears a little bit on what's going to work the best, we're going to have to start answering some of those questions. So now we're coming back to the present. That treatment stuff's all out there in the future because nobody's mandated to do it. It's just what might we be doing. But you may well have PFAS already impacting your utility. And if it's not already impacting it, it's probably going to happen soon. And so our dilemma is, if we end up with PFAS in some of our media, and that has become public news, well, we don't have a proven solution to say, well, don't worry, folks, we're just going to deploy X piece of equipment and it's going to take it all out. And secondly, we don't even have consistent regulations to tell us if we remove it to this level, then we can be comfortable with the level of risk we're asking our customers to assume in terms of health risk or whatever. And so what I wanted to spend the next little bit talking about is, okay, so if you're a utility operator, what do you do if you find PFAS in your media? And so I've kind of outlined our approach here and our thinking, but the first thing would be to say, don't panic. So one thing we can remember is that PFAS has actually been in our waste streams for a long, long time. Remember, these have been produced since the 1940s. There has been exposure to people for that long period of time. And so just because we're finding that it's there and we know that it's there doesn't mean that the impact is going to be different. So we recognize and we acknowledge that there are risks with PFAS, but it's also not a sky is falling kind of scenario. We've been dealing with it for a long time. It's going to take a long time to unwind it. And so hopefully we can inject some reason and some calmness into the discussion. And so the second item there, don't shut down. And there's really two aspects to this. The first is we talked about the biosolids disposal, beneficial reuse alternatives and so forth. And some of the systems that have been impacted by PFAS, one of their first reactions has been, we've got to stop land applying. We got to shut down our beneficial reuse program. And the reason we would recommend that you don't do that, at least not immediately, is that once you shut down a beneficial reuse program, it's going to be very difficult to get it restarted, to get it through public comment, to get regulatory acceptance and so forth. And so you're better off, in my opinion, that you continue to do what you're doing while you start gathering data. There's still a lot of unknowns out there in terms of quantifying what the impacts are, what the risks are, and so forth. And so we would recommend don't knee-jerk and shut things down yet. Let's step back a little bit. Let's gather some data. Let's look at how this situation develops. But the second piece of shutting down would be to say, we might be inclined to say, oh gosh, we can't even give them an answer. We don't have treatment technology for this. We can't even tell them what regulations we have to abide by. Maybe let's just be quiet. Let's not even talk about it because we can't say anything. And so we would recommend that you not do that. That really positive communication to your stakeholders is the way to go. And you might wonder, well, how do I even communicate anything positive? I don't have anything positive to say. I've got PFAS in my wastewater discharge, and it's impacting the environment, and I can't do anything about it. How can I get a positive out of that? Well, so we've got a couple of ideas here about ways that you can communicate some positive things to the stakeholders, and the ultimate goal being you can establish yourself as a trusted source of information and maybe help guide the narrative that's going on around PFAS in your community. So the first thing I would recommend is that you focus in your communications on customer safety. I mean, isn't that what you strive for right now in your treatment, whether you're a wastewater operator, whether you're a water utility operator? You want to produce the safest product that you can to discharge or to distribute from your facility. And you can communicate that is your priority, and it will be your priority with respect to PFAS going forward. Secondly, you can reaffirm your regulatory record. And that what that helps you to do is, even though you can't point to a PFAS standard and say, hey, we're meeting the PFAS standard, you can look at it and say, every standard that's been put on us, whether it's with respect to chlorine residuals or THMs or this regulatory program or that regulatory program, hey, we're meeting all those things. And that's our culture. And so you can be assured that as PFAS regulations solidify, we're going to be on top of that, and we're going to do what it takes to take care of it. The third item has to do with that idea of not shutting down if there's PFAS in your media. So you can admit the presence of PFAS there, and you can provide your data. Because remember, somebody's going to be able to get hold of that data whether you provide it to them or not, whether it's through FOIA, whether it's through third-party sampling or whatnot. There's really no way to keep a wrap on it once it's been detected. And so you're better off to be open about it and to provide that information out there. And you can help guide the conversation, because that's where this last item comes in. We can start providing perspective on what this PFAS contamination actually looks like. So we've talked a lot about parts per trillion, and we know it's a really small amount, but we've got a couple infographics over here on the right that just kind of help you put that in perspective of the way that people can understand it. So we've got a drop of water in 20 Olympic-sized swimming pools, right? We've got 1 second in 31,000 years. I mean, can you even conceive what 31,000 years feels like compared to 1 second? So you can help to decrease the level of panic in your stakeholders, to help inject some, dare I say, sanity, but really inject some calmness and some reasonableness into the discussion. And as I said, you can help shape the narrative around PFAS. And so you can communicate, your exposure to this is really small already, that we're focused on customer safety. And as soon as we've got some solid guidelines to act on, we're going to do it. We've proven that we are going to do it because that's been our record up till now. And in the meantime, here's what we found about PFAS. And then if you become that trusted source of information for them, you can be communicating out on a routine basis. You stay up with the issue and the scientific research and so forth, and then you can be a conduit that people learn to trust in this whole thing. So let's try to put a wrapper on. This question here. Methods for preventing PFAS from infiltrating groundwater. The only methods I could think would be you have to put it in a place where it's not going to be, where you can't leach it. So I can't think of a method that would be effective, for example, for land application of biosolids, because the whole point is we're putting it on the land and letting it degrade. Landfill may be a more positive solution to that, because your subtitle D landfills have to be lined and they're collecting their leachate and they're treating it. Although much of that leachate ends up back at the water utilities, right? So it may be you could do some lime stabilization or some other things, but we really just don't know very well about how to stabilize it in a format like that. So just to kind of summarize what we've been talking about. We were paying a lot of attention to pharmaceutical residuals 10 years ago, but now all of a sudden PFAS has kind of grabbed the attention of environmentalists, regulators, the news media. And so the pharmaceutical residuals have kind of faded from our attention. And the reason is that PFAS is in tons of things that we use on a daily basis. We've been finding it everywhere in our media. And we've identified it being resistant to degradation, and conventional treatment doesn't really touch it. And so the persistence in the environment is going to raise some concerns for long-term exposure to people. And so even though we have difficulty predicting what the eventual regulatory outcome looks like, we can predict that it's going to impact water utilities soon, if it hasn't already, and it's going to be something that's going to be coming for years. We don't know how to treat it yet. We're still working on treatment technologies, and we don't have a promising front runner. And so in the light of all that uncertainty out there, we have to have a strategy, and we believe your strategy for dealing with it in the immediate future is clear communication. You have the opportunity to become a trusted source of information for your customers and to help set the narrative around PFAS in your community.
Tom, we have two questions
Yes.
regarding activated charcoal and the other one about thermal hydrolysis.
Right. So activated charcoal, again, that's related to the granular activated carbon we talked about in terms of liquid treatment is a very similar product to that activated charcoal. So conceivably, you could probably incorporate that into biosolids. Mixing, and of course, the cost of the material could be a pretty substantial issue in how you actually carry it out. What was the second question, Mehmet?
The Canby process, thermal hydrolysis, is there any insight into what thermal hydrolysis can do for PFAS removal?
The main thing about the hydrolysis is the temperature. I have heard numbers as low as 350, 400 degrees that can be effective for PFAS. But in general, people are talking about that 1100 degrees C number for removal. And so if your process is getting up to that level, then I would feel confident that you're going to be able to impact PFAS. For lower temperatures than that, I suspect it's going to be a continuum. There will probably be some that it's effective for and others that are not. So again, that's going to be a subject for future research.
We have one more question, but I'm going to hold that to the end. We're running up against the hour. I think we can answer the question once we finish the slide.
Sure. And so wrapping up with this idea of becoming a trusted source of information, we've provided here some resources to at least get you started if you want to explore some more. And we can email this information to you so you don't have to copy it down from here. But EPA has some general summary information, and then these other organizations are kind of at the forefront of communicating some of the risks and the regulatory frameworks and treatability. In particular, the Interstate Technology Council has got a lot of good information on treatment technologies, where they've been deployed, what scale they've been deployed at, and so forth. And so with that, we can open up the Q&A.
So we have two questions already queued up. if you have any more questions, Zoom has a function to raise your hand. You can go ahead and raise your hand and I will call on you. But let's start with the two questions that came in through the Q&A already. The first one is PFAS in regard to photography. Can you elaborate?
So, yeah, so this would not relate to digital photography, but it would be more along the lines of there's still development of prints, and there are still some, particularly in the professional photography community, who are using the traditional film approach. And so I believe it's components in film. And so the risk there is really more to the user, someone who might be developing the film or using the film for photography or movies or whatever. So that's the best I really know about that at this time.
Okay. And the next question is about, the question is, what are the chances of replacing PFAS with less toxic substances?
So I think there are some good opportunities to do that. For example, that's one of the reasons why the industry is phasing out the PFOA and the PFOS chemicals and moving to other ones. The focus is not only on reproducing the characteristics and the performance of those things, but they're certainly interested in the less toxicity. And there are some PFAS compounds that are less toxic than others. And so that certainly will be a direction that I believe the industries will be moving, particularly as they are becoming subject to regulatory and perhaps even civil actions that are going to start costing them money. They're going to be paying a lot of attention to those types of things. And I think that's going to be one of our greatest opportunities, honestly, with respect to PFAS.
Great.
And to add to that, the issue right now is basically what's going to happen to those components that has already been released into the environment. And as we learned that it's strongly persistent in the environment, and now we are trying to look for ways to get it out of our water sources. So even though we're phasing out those harmful chemicals, their presence in the environment is still there. And it's a source of concern to the researchers.
Hatem, going back to the question we had earlier regarding the pesticides, did you want to elaborate on your answer?
Yeah, so according to the ITRC, the Interstate Technology Regulatory Council, they noted that the PFAS is used in biocides and pesticides or herbicides as either an enhancing agent or an anti-foaming agent in the pesticide solutions. So that's basically just to improve the quality and the effectiveness of these chemicals.
Very good. I don't see any raised hands, and I think we're almost out of time. If you have any further questions, you may email either Tom or Hatem at their KCI email addresses, and that will be thomas.volmar@kci.com or hatem.fadlala@kci.com. The speaker's names and the spelling is in the flyer. We can also send you the contact information once we're done with the webinar here. So this wraps up today's webinar. Thank you all for attending today's session. We look forward to seeing you all during the next session on October 8th, and the topic will be fish passage. You will soon see an advertisement for the October seminar. You'll be able to register using the same platform that we're on right now. Before I say bye, I see that there are two more questions. Let's take a look real quick. All right, the first one is, what about analytical methods for measuring PFAS? My understanding is that EPA hasn't yet developed an official lab method.
Yes, I'll tackle that one, Mehmet. So there actually are there are several official lab methods that are now accepted by EPA, but it only covers a handful of them. There might be a dozen PFAS chemicals that even have accepted lab methods for them. And that's one of the additional challenges that we have. Once these methods continue to be developed, we may be finding PFAS family members that we didn't even know about. We may be able to identify risks with them better. And so there's going to be this expanding landscape of PFAS chemicals that we're able to detect, but right now it's a very small sliver.
And the next question is kind of related to what you just said too. This is from Kamal. He's asking, with thousands of PFAS chemicals, how many are detectable using current technologies?
Right, and certainly in terms of the environmental concentrations of parts per trillion, as I said, it's very few. It may be a dozen or 18, something like that, that can be detected. Now, in a method like GCMS, gas chromatography and mass spectrometry, you can see the compounds in there, but it's difficult to quantify the amounts that are in there, and there may be interferences with a lot of other compounds. And so that's what these new methods tend to be developed out of. They start finding them, using spiked solutions and whatnot, and then they'll start refining how they can separate those from other chemicals that might be in the mixture. So that's a long process as well.
Very good. Well, I don't see any more questions, so we'll go ahead and wrap it up. Again, thank you for your time, and we look forward to seeing everybody again.